Okay, so this time we've got this question here. Draw a graph for a radioactive source with decay constant lambda equals 0.132 seconds to the minus 1. And it gives us the original number. So the first thing we need to do is produce a table of data. So we've been told to calculate the number of undecayed nuclei after every second. So I've done that here. Well, how have I done that? Well, let me just give you an example for this one here. Okay, well, we know that for 0 seconds it's that. After 1 second, we can say that n equals n naught e to the minus lambda t. So it's just n equals 2000 multiplied by e to the power of minus 0.132 times 1 second. Okay, and if you put that into your calculator, you can see we just get 2000 times e to the power of minus 0.132 times 1. That gives you 1753 when you round it up. Again, if you do that for, let's say, we'll do that for 8 seconds now. It's just 2000 times e to the minus 0.132 multiplied by 8, which gives you 696, okay, which was that value there. So that's how you do it. You just calculate values for each of those. And then we can plot a graph of these values. Okay, so obviously you're going to need to do that on graph paper and work out your half-life. And then once you've done that, you're being asked to work out whether it matches up with the calculated value. Now, this brings out an important point here. We can calculate the half-life of something using this equation because we know that n equals n naught e to the minus lambda t. When time is equal to t half, we know that n is equal to n naught over 2. Okay, so if we write our equation here, we can write this. N naught over 2 equals n naught e to the minus lambda multiplied by the half-life. When time is equal to the half-life, we know that the original number of nuclei have decayed to half their value. So if we divide both sides here by n naught, we can cancel those out, and you get half is equal to e to the minus lambda multiplied by t half. Okay. What we can do then is natural log both sides of that. So ln of a half is going to be equal to minus lambda t half. So if you natural log 0.5, so let's take the calculator, natural log 0.5, that's going to give you minus 0.693 is equal to minus lambda. Now we already know what lambda is. It's 0.132 multiplied by t half. Okay, so if I go up here to work this out now, finally t half is just equal to minus 0.693 divided by minus 0.132, and that's going to be equal to 5.25. Okay, now what you need to do then is plot your graph and figure out, do you get a similar value for half-life? Now, having completed this question, or the first part of it anyway, obviously you need to draw the graph, but don't forget when calculating the half-life you need to include a unit, and this is a time. The half-life is a time, so the unit is seconds. Okay, so it's 5.25 seconds. So here you can see I've plotted the number of undecayed nuclei against time, radioactive decay curve. Sorry about the slightly wonky line of best fit or curve of best fit. So I've plotted that. This is our original number of nuclei, n naught here, isn't it? Okay. So after one half-life, we know that N naught obviously halved, and that's going to give us 1,000. Okay, so after one half-life, we're down to 1,000 nuclei. We find that, we draw across and come down here, and we'll find that the half-life comes out as 5.2 seconds, okay, which is very similar to the value that we calculated when we did the question and used the numerical calculation.